This is problem 9.76. It is about a pulley with two masses A and B, with mass A being higher than mass B and having a bigger mass as well. What's new in this problem is that the pulley is able to rotate from the contact it has with the rope, and they tell you that the rope does not slip or break. Everything is initially at rest, and they want you to find the speed of A when it hits the ground. They tell you that there is no friction, and like every other physics problem, the first thing you have to ask yourselves is, what type of problem are we dealing with? F equals ma will be far too complicated for this, so we're going to use energy to solve this problem. The caveat is you need to recognize that there are three types of energy in this problem. There is the kinetic energy from the center of mass moving, and we call that linear kinetic energy. There is a gravitational potential energy, and the new thing that you introduced to in this chapter is rotational kinetic energy. Like every other energy problem, we're going to do some accounting. We'll write down the initial energies and the final energies. The linear kinetic energy is due to the center of mass moving. Since initially everything is at rest, then all three bodies will have a linear kinetic energy of 0. Later on, we will see that A and B will have some at the final. For potential energy, there is no elastic, only gravitational. The gravitational potential energy of A is MAGH. For the pulley, we'll call it some mass MP and some height HP from the ground. As we will see later, we can even skip this because this potential energy does not change from initial to final. For rotational, all three have 0, since everything is at rest. So we combine all these energies to get a final expression for the initial energy. So now we do the same thing but for the final stage. So the final stage, both A and B are moving their center of masses. So both A and B will have some linear kinetic energy. Now the pulley's center of mass is staying at the same spot, so the pulley's kinetic energy from the center of mass will be 0. And I write the expression for B. For the potential energy, A will be at the ground, so it will have a potential energy of 0. The pulley will still have the same potential energy, MPGHP. And B will have a potential energy of MBGH. Now for the rotational, A and B are now rotating, so they will have rotational kinetic energies of 0. But the rope, however, is allowed to rotate. So it will have a rotational kinetic energy of I, which is the moment of inertia, time omega, which is the angular velocity, and that will be squared over 2. So once again, we combine all of these expressions to get a expression for the final total energy. Now on purpose, I'm just going to keep the expression for the moment of inertia, because in this problem they could have given you, say, a hollow sphere or some other geometry which have a different moment of inertia. But everything in the problem would be solved exactly the same way. Right, and next, a very important concept is about the rope not slipping. What this tells you is that at the top of the pulley, the rope and the pulley at the top move at the same speed. So the speed of the pulley at the top must be equal to the speed of the rope. And this is important because we need this to be able to relate the angular velocity of the pulley to everything else in the system. So we know that angular velocity is equal to, we know that the velocity tangential in the circle is equal to r times omega. And we say that this has to be equal to the speed of the rope, so the angular velocity is the speed of the rope over r. Since the rope does not break, this also means that the speed of A has to be the same as the speed of B and the same as the speed of the rope. So at the final moment, the angular velocity of the pulley must be equal to the final velocity over r. And that is the final velocity that we're trying to find. I'm sorry, the final speed. It will be the same speed that A and B will have. Alright, so I set the two energies equal to each other with all these expressions. I recognize that MPGHP, the gravitational potential energy of the pulley, is the same, so I'm going to be able to cancel those out. And that the final speeds of the rope and masses A and B will be the same. And the angular velocity final will be the final speed over r. So once again, I'm able to cancel out the potential energy of the pulleys because it's the same initially and final. So when you do these type of exercises, if there's anything that is at the same height, you can just ignore its potential energy. Alright, so substitute the final speeds of A and B with the same final speed, and then substitute the angular velocity with the speed over r expression we had before. And then we just do a bunch of algebra to be able to find the final speed. So this is a long problem indeed, with multiple steps. But at the end it just came to a few concepts. One, that it was an energy problem. Two, that there was going to be some rotational kinetic energy at the pulley. And that if the rope does not slip, then the velocity of the pulley at the top has to be the same as the velocity of the rope. And then solve for the angular velocity that way. So altogether, we solve for speed, we get the following expression. We'll get that it is proportional to the difference of the masses, ma minus mb. If they were the same mass, then nothing would happen. There would be no speed that would be picked up. And of course, for this expression to make sense, A has to be bigger than B. And the bigger A and B are, and the moment of inertia of that pulley, then the less speed A and B pick up at the end. So this is your final expression. And I leave I this way so that if it was another geometry, like a hollow pulley or whatever they want, everything would have been done the same way. Alright, let's recap. This is indeed a long problem with a lot of concepts. So once again, it is two unequal masses on a pulley, but this time the pulley is able to rotate. And they tell you that the rope does not slip. Information that will allow you to relate the angular velocity of the pulley to the final speed of the masses. Like every other physics problem, we ask ourselves what type of problem is it. We know it's an energy problem, so we'll have to use different types of energy. We use the linear, potential, and rotational, write expressions for the total initial energy. And remember that we don't have to write down the potential energy of things that stay at the same height. Then we repeat for the final energy. We know that the rope not slipping means that the velocity at the top of the pulley has to be the same as the velocity of the rope. The rope does not break, so it relates the speeds of A, B, and the rope, and give us a final expression for the angular velocity. Then we do a bunch of algebra and solve for our speed squared. It's a long problem, a lot of useful concepts. I hope this was useful. Have a beautiful day, everyone.